In this section we are going to talk about graphing functions, and we're going to just touch the surface of this. So there are going to be in later sections some things where we're going to take this a little bit further and use different properties. So let's look at what we mean by the graph of a function. So as we mentioned before, one of the four representations of a function that we're going to look at are graphs of functions. And so a graph of a function f of x with domain A is the set of all points x comma f of x where x is an element in A. And so there's different ways we can graph a function. The first is point plotting, which we'll talk a little bit about in this video. There's what we call graphing tools. So you can use technology. There are graphing plotting mechanisms on the computer or in the web. There's also graphing calculators and things like that. I'm not going to spend a lot of time on that because in this class and in most of the future classes that you'll take, we are not going to allow calculators. We want to know that you know the basics for these. There's using basic functions and transformations, which we'll talk a little bit more about in this chapter. And then there's using just properties of functions to get the graphs. And we'll see that in some of the later chapters. Okay. So in this first example, we're going to just reiterate what we mean by point plotting. So given a function, so in this case f of x equaling minus x squared plus 3x, if we want to graph this using point plotting, then I just want to find ordered pairs x comma f of x where those values are in the domain. Okay. Now again, depending on what values you pick, will determine what part of the graph you're looking at. And you want to be able to extend that so you get a general picture for the graph. Now, when you go to point plot, I would suggest picking three types of numbers: positives, negatives, and 0. Okay? In some cases, your function may be of the form that some of those don't work, and so then you want to try some of the rational numbers, or more, maybe more positive or more negative, just depending on what the function looks like. But you should in general try those types of numbers to get a general picture for the graph. So again, to point plot, I'm going to start by listing my table of values here so that I can pick ordered pairs to put on my graph. Okay. And again, choose a couple of points. I would say 1 or 2 is not enough. 3, if it's a linear equation, you'll probably have enough to get the figure. But I would say as you're point plotting, pick a minimum of 5 points. And again, spread those out. Don't pick all positive or all negative. Spread it out across the origin. Okay? In some cases, you may need more points than that, and we'll look at some examples of those in a minute. Okay? So here, I'm going to take again every x value, plug it into my function, and find out what the range value is. So here, if I plug in a -2, I'm going to get -4 minus 6, which looks like a -10. At -1, plugging that in, I'm going to get -1 minus 3. At 0, we can see that that's going to be 0. At 1, I'm going to get -1 plus 3. And at 2, I'm going to get -4 plus 6. Okay. So there's kind of what my graph is going to look like. Okay. Again, when I go to graph, I want to start by labeling my function, my picture. And then we'll go ahead and just plot the points. I'm just going to use a different color so you don't get it confused with my coordinate system there. So at -2 when we plug in, again we're getting a -10, so down here. At -1 when I plug in, I'm going to get a -4. At 0, we're at 0. At 1, I'm up here at 2. And then at 2, I'm also here at 2. Now, again, in general, I could probably figure out where this is going, but this may be one where I want another point or two, okay? Because I can kind of see the general shape of the graph, but again, for point plotting, I want it to be something that gives me kind of a full picture of the graph, okay? In this case, I can kind of see it goes here, but then does it taper off? Does it come back down? Does it go back up? We need some other information here. And a lot of graphing is inference, meaning I'm going to look at what I have on there and infer some details about the remainder of the graph. For example, in this inference, I can look and see that on this side, I'm probably going to infer that it goes down to -infinity from there. And we could check that with looking at, say, -3 or -4. Okay. In this case, because of the nature of most graphs, or most functions, I know that if I pick points in between 1 and 2, I'm going to get a value that is either less than 2 or bigger than 2. And by the way this pattern is going, it seems like it should get bigger and then go back to 2. And we can check that by looking at, say, 3/2. And then for the remainder of this, well then if I check something like 3, and I'm going to put this in black so you can see that we did it after, if I picked something like 3, I get -9 plus 9, which is 0. So I can see it's going to come back down here, and again if I picked other points I can infer that it's going to decrease to -infinity. So there's an example of point plotting to get your values for your graph. Okay. Now, this type of function that we're looking at here is what we consider a quadratic. And we'll talk more about quadratic functions later. Okay. There are other types of graphs that you're going to be asked to look at as well. And so obviously there's the linear that you're probably most familiar with. One of the ones that some people are not as familiar with are your piecewise defined functions. Okay? And their name tells exactly what it is. I'm looking at a function that is defined in pieces. That means when I go to look at the graph is also going to be in pieces. Okay? Some of those pieces may connect, but not always. Okay? In a piecewise defined function, these here give the pieces of the function. These here give your domain pieces. Okay? That means when I'm looking at this piece, meaning the 3x minus 2, I'm only going to consider that on the domain x greater than 2. It doesn't matter that the domain for that function is all real numbers. I'm only going to consider it on that piece of the domain. Same thing for this one. If I look at x squared plus 1, that function piece, I'm only going to consider it on the domain x less than 2. Okay. So when I go to graph this, I can still point plot if I'm not sure what these pieces look like. If you know what the pieces look like, you can just graph them for their domain. Okay, so this first one, I'm going to look at g of x equaling 3x minus 2. And I'm going to come up with some ordered pairs. Okay, Now the ordered pairs I choose here, unlike in the last case where I'm picking positive, negative, and 0, here I want to pick them so that they're within the domain. So I need things greater than 2. Now one of the things I suggest is always starting with that boundary point, because I need to know what happens where the graph starts. Okay? So if I'm looking at 2 and then things bigger than 2, so 2, 3, and 4, there's a couple of good points. Again, you can choose more of them. At 2, we can see we get 6 minus 2, which is 4. At 3, 9 minus 2, which is 7. And 4, we get 12 minus 2, which is 10. Okay, so I'll be able to graph that piece of the function. Then I'm going to do the same thing with the other piece. So here, if I look, for x squared plus 1, I want them when they're less than 2. So again, I'm going to start at that boundary point and pick values less than 2. Again, you can pick more points if needed. So plugging into here, we see 4 plus 1. At 1, we get 1 plus 1. And at 0, 0 plus 1. Okay. So to graph, again, I'll start by labeling my graph. So in my graph, I can see I'm going to start at 2. Notice at 2 for the 3x minus 2, the domain is strictly greater. So it's non-inclusive. So at 2, when the value is 4, I'm going to have an open circle for the non-inclusive. Okay. Then at 3, I'm at a value of 7. And at 4, I'm at a value of 10. So I can see that my graph there is doing that for the values bigger than 2. For the pieces less than 2, same thing. At 2, I'm at a value of 5. Again, it's non-inclusive, so I'm going to have an open circle. At 1, I'm at 2. And then at 0, I'm at 1. Now this one, you almost want to draw a straight line like we just did, but this one again I might need a couple more points. So for example, if I look at negative 1 and I plug in, I see that I also get 2. So this one is actually doing something like that. So our graph for this one looks like part of this parabolic shape and part of that straight line. Okay. Again, it's in pieces because it's a piecewise defined graph. Another function that you're going to look at is the absolute value function. And this one I do right after piecewise because it's considered a piecewise function if I look at the graph. So if I consider the absolute value of x based on the definition that the value is x when x is greater than or equal to 0, and when it's negative x when x is less than 0, then if I look at this graph, then for all the x's greater than or equal to 0, I'm going to get exactly the x value. And if I look at the opposite of that value, when it's less than 0, then there's a picture of what our graph is going to look like for the absolute value. Okay. It's two pieces, but again, they combine together. Okay. If I look at, for example, f of x equaling absolute x plus 4, then again, I can think of this as a piecewise function. It's going to be x plus 4, so the positive of that, when x is greater than 0, but more importantly, when x is greater than negative 4, and on this side, if I take the negative of that, when x is less than negative 4. So here again, if I go to graph it, for this one at negative 4, I can see I'm going to be at 0. That one's inclusive, so closed circle. If I put in things bigger than negative 4, so for example, let's do negative 2, I can see it's going to be at 2. At 0, I can see it's going to be at 4. I'll do one more. If I do 2, we can see it's going to be up there at 6. So there would be that upper piece of that curve. And then for the lower piece, I can do the same thing. It's going to be negative x minus 4 when x is less than negative 4. So again, at negative 4, we can see a negative of negative 4 minus 4 is just 0. So it's going to be at that point. At, say, negative 6, I'll get 6 minus 4, which is 2. And I didn't draw this over here, but we could look, if I extend this out, if I do negative 8, you can see that's 8 minus 4, so that would be up here at 4. So there would be my absolute value curve. Now, in addition to these two piecewise functions, there are other types of functions that you're going to look at that are kind of the special cases. And your book talks a little bit about greatest integer functions, which I'm not going to go into, but it's worthwhile to at least look at. Okay. One of the other things that is important to understand about graphs of functions is this notion of what we call the vertical line test. This is useful in determining if a graph of a function, if a graph is a function. Okay? Sometimes you're going to be given the picture before you're given the algebraic form or the numerical form or, the words. Okay? So you may only see the picture and you need to be able to determine whether or not you're looking at a function. Okay? So the vertical line test says that for every vertical line that passes through a graph, if the line touches the graph in at most one point, then the graph is a function. And again, at most one point means it may not touch the graph at all, but if it does, it can't touch in more than one spot. Okay. And so here we've got a couple of different graphs, and we can just see if I take vertical lines and start putting vertical lines on these graphs. In this case, I can see that it doesn't matter where I put it, they're only going to touch in one spot. So this is the graph of a function. Okay? Same thing here. If I take vertical lines and start putting that on the graph, I can see that this is going to pass, so this is also a function. Okay? In this case, there are points that I can put the vertical lines where it's touching it at most one point, meaning no points, but there are also points where it touches in more than one point. And so this is not a function. Okay. And at least for now, we're not going to worry too much about things that aren't functions, so this is why we need to be able to determine whether or not they are. Okay, there are going to be some things we do later, so for those who go into Calc 2 or even Calc 3, you're going to be looking at things like this that may not be functions, but we still want to be able to do things with them. Okay. And then we have things like this graph where maybe the domain is not all real numbers, or it's broken off in pieces. And so again, all I'm caring about is whether or not, as I draw those vertical lines, when they touch the graph, do they only touch in one point? And in this case, the answer is yes. So we can see that this is also a function. So lastly, we should look at some of the basic functions. So as I said, some of the things you're going to be asked to do are to graph functions from their basic curves, or to use transformations of functions to graph them. And so in order to do either of those things, you have to know what the basic functions look like. And so here are some of the basic functions, and for these I would suggest knowing what the basic equation looks like and what the basic corresponding graph looks like. Okay? So the first of these are our linear functions, and there's two types of linear functions. The first is just one that's a horizontal line, y equals b. So wherever b is on the y-axis, the line that goes through that point would be our first linear equation. Okay. Y equals mx plus b, this is just our general equation for a line. So not necessarily horizontal, but something with a slope that again passes through the point b. Okay. In this picture, the way I've drawn it, m is positive, but we could also have where it goes through b and m is negative. Okay. The next group of functions that we'll look at are power functions. And so these are the things where we take our variable and raise it to a power. So things like y equals x squared. This is just a basic parabola. Y equals x cubed, I think of as the chair function. It almost looks like you can sit in it. Y equals x to the fourth. Now this one looks a lot like your parabola. The only difference is it's got a flatter bottom. Okay? And the power functions keep going. So I could have x to the fifth, x to the sixth. And what you'll find is as the power increases, this middle piece around the origin gets flatter. So if I look at x to the fifth, the only difference is it's going to go out a little more before it decreases or increases. Okay? And x to the sixth would look like this, except it's going to be a little bit more flat out here. It's going to square out the bottom. Okay. Our root functions, so these are kind of the inverses of our powers. So instead of raising it to an exponent, I'm going to root it. So take the square root. For the square root function, this one has a restricted domain. So remember, we can't have negatives under the radical. So it's going to start at 0 and look like half of a sideways parabola. For the cubic, so your odd roots, remember I can have negatives in there. So here, what we're going to see is kind of both halves of it. And then the same thing is true here. As my root increases in power, so if I look at fourth root or fifth root or etc., then what happens is on this y-axis, it's going to get a little flatter. So my fourth root is going to come up a little more before it comes out. And same thing here with the fifth root. It's going to come down further before it comes out and up further. Okay. For our rational or reciprocal functions, so this is where I'm going to take my variable and put it in the denominator. So the 1 over x, this is one of the first functions where not only are my domain and range restricted, but I have asymptotes, meaning the restrictions on the domain and range aren't just places where it's undefined, it's places where my function gets close. Okay, so there's my 1 over x, and then the other is the 1 over x squared. And again, both of these will be important later on. The 1 over x squared looks very similar, except that because of the square, both the positive and negative sides look the same, or reciprocated, and reflected. And then the absolute value function, we've looked at this one recently, so y equals the absolute value of x. That's our v. Okay. So there are our basic functions. And again, when I say basic functions here, I mean given these exact equations, this is what they look like. And we'll talk about transformations of these in the next few sections. So if I wanted to graph, say, a 2 over x squared, what does it do? Or if I want a negative 1 over x squared, we'll talk about those types of transformations.